Hello everyone. The topic for my presentation today is energy applications of nanotechnology. We have divided the topic into three terms: commonly used nanomaterials in energy, nanostructures in energy, and application. So the first part will be taken by me and the other two parts will be taken by my group members. I have divided my content into introduction, graphene based materials, silicon based nanoconductors, and nanocellulose based materials. As the world's energy demand continues to grow, the development of more efficient and sustainable technology for generating and storing energy is becoming increasingly important. People in the fields of science and engineering have already begun developing ways to utilize nanotechnology for the development of consumer products. Benefits already observed from the design of these products are an increased efficiency of lighting and heating, increased electrical storage capacity, and a decrease in amount of pollution from the use of energy. If we talk about the energy, nanotechnologies provide the potential to enhance energy efficiency across all the branches of industry and to economical leverage renewable energy production through new technological solution. So we have an energy source, and then energy source is converted and there is a conversion of energy. Further, that energy is distributed and stored and then used. So if we look at the diagram, we can understand nanotechnologies provide essential improvement potentials for the development of both conventional energy sources and renewable energy sources like geothermal energy, sun, wind, water, tides, and biomass. Further, talking about energy conversion of primary energy sources into electricity, heat, and kinetic energy requires at most efficiency in fossil fired gas and steam power plants. It would help to avoid considered amount of CO2 emission. Higher power plant efficiencies, however, it requires higher operating temperature and thus heat resistant turbine materials. Energy distribution is the reduction of energy losses in the current transmission. Hope exists that extraordinary electric conductivity of nanomaterials like carbon nanotubes can be utilized for application in electric cables and power lines. Furthermore, the nanotechnological approach of the optimizing superconductive materials for losses of electric conduction. And lastly, if we talk about the energy storage, the utilization of nanotechnologies for enhancement of electrical energy stores like battery and supercapacitor turns out to be downright promising. Due to the high cell voltage and the outstanding energy and power density, the lithium ion technology is regarded as the most promising variant of electrical energy storage. Nanotechnologies can improve capacity and safety of lithium ion batteries. For example, through new ceramic, heat resistant, and still flexible supercapacitors and high performance electrode materials, the companies have been pushed to commercialize of such systems for the application in hybrid and electric vehicles as well as stationary electric storage. Commonly used nanomaterials in energy. There are numerous numbers of nanomaterials that have been used today for the storage and production of green energy. But the most commonly that has been used since decades are graphene based materials. There is enormous interest in the use of graphene-based materials for energy storage. The research on use of graphene for energy storage began very recently, but the growth rate of relative research is rapid. Due to its high surface area, large electrical conductivity, lightweight characteristics, chemical stability, and high mechanical flexibility, graphene can increase the energy capacity, charge rate, and stability of lithium ion batteries. In practicality, the lifespan of and recharging time of the batteries used in electronic applications, ranging from electric vehicles and mobile phones to laptops, could significantly improve. Among various organic and inorganic materials, graphene exhibits strong potential to have to energy demand in various ways. Graphene and its various composites can also be used in supercapacitor to enhance power density and rate performance. Graphene is actually the main source to obtain a single atom layer, two-dimensional plane called graphene. Graphite is the main source to obtain the single atom layer, two-dimensional plane called graphene. The use of graphene can be classified into two broad categories: energy storage devices and energy conversion devices. While it remains to be seen how graphene can transform the energy industry, its journey has only just begun in creating new opportunities for application in energy storage and energy conversion. It seems likely that graphene and related materials could be exactly what it needed to help engineers to find renewable alternative for traditional material to develop next generation energy devices. Next we come to silicon based nanosemiconductors. Silicon based nanosemiconductors has changed the definition of nanosemiconductors. Silicon nanoparticle is fascinating area of science and one of the significant technology implications. They are generally considered as non-toxic and have good biocompatibility. They utilize silicon nanoparticle in order to absorb a greater range of wavelengths from electromagnetic spectrum. This can be done putting many identical and equally spaced silicon rods on the surface. In the field of storage sensors, silicon nanoparticles are promising materials in various applications due to their unique properties like large surface area, biocompatibility, stability, excellent optical and electrical properties. The arrangement of silicon particles allows solar energy to be reabsorbed by many different particles, exciting electrons and resulting in much of energy being converted to heat. Then the heat converted into electricity. Lastly, coming to nanocellulose based materials. Nanocellulose offers a unique combination of properties including flexible surface chemistry, transparency, low thermal expansion, high elasticity, anisotropy, and the ability to bind the other conductive materials, enabling extensive application in the flexible energy storage devices. According to differences in raw materials, preparation method, and morphology, nanocellulose can be divided into three categories: cellulose nanocrystals, cellulose nanofibers, and cellulose microfibers. There is one more category called bacterial cellulose. Integrating nanocellulose into energy-related devices would definitely inspire researchers in the area of eco-friendly materials, and we find it very promising to address the important environmental concerns. In the past few years, the application of nanocellulose has been related devices have been focused on batteries, sensors, and other electronic systems. But the current focus is on sustainable supercapacitor, which is fast growing and with very high progress rate. Nanocellulose derived carbon materials also are increasing interest in the sustainable energy storage due to their low cost and raw material abundance, high conductivity, and rational electrochemical performance. So, these are some of the popular materials that have been used for the energy, for the green energy in the environment. Thank you. The further will be continued by other group members.
I am Shirish Killeda. I am going to deliver presentation on energy applications of nanotechnology, and my part is nanomaterials and nanostructures in energy. So one-dimensional materials. One-dimensional nanomaterials are widely explored with the aim to enhance the energy harvesting efficiency and to enable the flexible nanogenerators due to their superior light absorption, excellent electronic conductions, and high mechanical strength and ultra-low thermal conductivity. The advantages of porous one-dimensional nanomaterials for energy storage. The advantages include the smaller crystal size increases the utilization of active materials, resulting in enhanced specific capacity. The porous one-dimensional nanostructures provides greater surface area than that of a non-porous system. High surface area ensures effective contact of the electrolyte to the electrode surface, facilitating charge transfers across the electrode-electrolyte interface. The ion diffusion length is further shortened since creating porosity in one-dimensional nanomaterials can effectively decrease the ion transport dimensions. The pores in one-dimensional nanostructures are usually continuous, which offers interconnected ion diffusion pathways through the electrolyte to the active material. The empty spaces in porous one-dimensional nanostructures accommodate the volume changes associated with the electrochemical reaction, thus limiting structure degradation during cycling. The porous one-dimensional nanostructures can assemble into interconnected networks, avoiding the use of binders and lead to freestanding flexible energy storage applications. The pores or hollow regions in the porous one-dimensional nanostructures can act as hosts for filling with other materials and enable multifunctional applications. In this slide we can see the nanotubes, nanowires and nanorods as well as quantum dots and nanoparticles. So regarding the quantum dots, I would like to say that the quantum dots are tiny semiconductor crystals which have the potential to convert the high energy photons present in the incident light into multiple electrons. And usually they produce the 3 electrons when every photon of sunlight hits the dots. Regarding the nanoparticles, I will say that in solar cells, bulk silicon is converted into discrete nano-sized particles. These particles will show distinct colors depending upon their sizes. Films of, films of 1 nanometer blue fluorescents, films of 2.85 nanometer fluorescent silicon nanoparticles, and they produce large voltage enhancement with improved power performance. The carbon nanotubes incorporated toward titanium oxide nanoparticle based solar cells provides a direct route, that is the escape route, to the electrons moving toward electrodes. Collect these electrons and show them in distinct path, which is shown in red line. So these are some fundamental properties of one-dimensional nanomaterials for energy applications. First property is electrical properties. Due to the quantum confinement of one-dimensional nanostructures, electron can flow efficiently in the axial direction without much scattering in the radial directions. In this case, the electrical properties should get improved theoretically as compared with their bulk counterparts. However, there are still several key factors which can practically affect the carrier mobility, such as crystal defects, diameter scaling, surface states, surface roughness, and configuration of the heterostructure utilized. Second property is optical property. Because of quantum confinement, optical properties of one-dimensional nanostructures can also be easily tuned by controlling the diameter and shape, which are especially important in the application of solar cells. In photovoltaics, one-dimensional nanostructure-based anti-reflection layers are usually fabricated on the top of the active layer in order to boost up the photon collection efficiency. The third property is thermal property. The fundamental thermal properties of one-dimensional nanomaterials are extensively explored for the thermoelectric and pyroelectric generator applications, in which an electrical potential can be generated by the temperature difference applied in the nanostructures. For most thermal properties, nanomaterials show significant variation from their bulk counterparts. Another well-known difference in the thermal properties of nanomaterials is the reduction of their melting points due to the high surface to volume ratio. The thermal conductance of nanowire material is also found to decrease with the reducing diameters. All the modulations in the thermal conducting of nanowires can be utilized for a wide range of applications in thermoelectric generators. The fourth one, last one property is mechanical property. The mechanical properties of one-dimensional nanostructures such as Young's moduli and resonance frequency can be assessed accurately by using the resonance atomic force microscopy or STEM. Because of the high surface to volume ratio, smaller diameter nanowires would have higher surface tensions, which increase the elastic modulus drastically for the cases of silver and PB nanowires. ZNO nanowires also display the diameter independent modulus while the strength is increased 40 times more than their bulk counterparts. Appropriate nanomaterial composites and their geometrical dimensions are essential for the flexible and variable piezoelectric generators. So these are some one-dimensional hybrid structures for energy applications. So in that we will decide the CU-GDNO nanorod structures. The nanorods are typically length 10 to 20 nanometer to overcome, and some of the 20 nanometer and have the advantage that can be made of metals, non-metals or mixed compounds. To overcome this, the advantage of this nanostructure include enlarging the light utilization rate by shifting the light absorption to the visible range, maximizing the specific surface area for mass transfer and reactant access by creating porous interior spaces. Due to these hybrid nanostructures, 1700 microgram mole per gram per hour H2 production is obtained. See, the second is CDS nanorod by mixing cadmium nitrate. The efficiency of CDS nanorods as photocatalysts for hydrogen production can be affected by the fast recombination of the photogenerated electron hole pairs and the photo's instability due to its high tendency to be oxidized by the photogenerated holes. To overcome these limitations, these catalysts were modified by adding molybdenum carbide. MO2C has high elastic conductivity and high catalytic properties compared to other PT group metal carbides. The third is TiO2Bi2S3 composite. TiO2 nanorods can be synthesized by Sol-Gel method. After that, Solotherm method procedure can be used to incorporate different amounts of bismuth sulfide Bi2S3 onto the surface of the nanorods. The last is piezoelectric and thermoelectric materials also can be used in the energy storage. The piezoelectric effect is the ability of some materials to produce an electrical charge in response to applied mechanical stress. This effect is reversible. ZNO nanowires are characterized by a hexagonal structure with significant anisotropy along the C-axis and perpendicular to it. The application of stresses on this material gives rise to a piezoelectric effect. When the curvature of the material is caused a displacement of the cations and anions that form the nanowire structure takes place, which cause the appearance of a dipole that macroscopically will cause the appearance of an electrical potential. This effect also can be observed in GAN, IAN, CDTE, CDAC materials. This is a nanocatalysis process in which the esterification of fatty esters into biodiesel occur. Heterogeneous catalysts that are fragmented into metal nanoparticles so as to speed up the catalytic process. They have an increased surface area. They can be easily separated and recycled. The trans-esterification of fatty acids into biodiesel. The base catalyzed trans-esterification reacts lipids with alcohol to produce biodiesel. The nanocatalyst pairs are also used to replace the commonly used sodium methoxide as base catalyst. The process is economical and recyclable, reacting at mild temperatures and pressures. Third, the producing cleaner biodiesel. And fourth one is greatly reducing water consumption and environmental contaminants. The nanoparticle technology triples the production of biogas. The biogas plus involves application of nanotechnology to improve biogas production. The controlled introduction of iron oxide nanoparticles in organic waste treatment can increase the production of biogas up to 3 times. Iron oxide nanoparticles feed the bacteria and enhance the biological efficiency. So these are the energy harvesting by ZNO nanostructure involves the introduction, properties, application, and properties. The introduction, the semiconductor materials and piezoelectric materials is involved. The properties of ZN involves the one-dimensional and two-dimensional forms of ZNO nanostructures, ability to control the synthesis of various ZNO nanostructures, wide band gap that is 3.37 electron volt, biologically safe and environmentally friendly. The application involves ultraviolet lasers, light emitting diodes, field emission devices, high performance in nanosensors. Doping of various ferroelectric materials into the ZN nanowires and using in huge industries can be a opportunity. The two-dimensional nanostructures for energy applications involve the graphene. Graphene is a one-atom thick two-dimensional carbon crystals in which sp2 bonded carbon atoms are packaged in a hexagonal lattice resembling honeycomb. The graphene shows many unique properties such as theoretical surface and high modulus elasticity and good thermal and electrical conductivity. The large specific surface area and good electrical conductivity make it very attractive as a platform for electrocatalytic applications. So these are the graphene and graphitic carbonate are also the form of two-dimensional nanometer which can be used for the energy application. The graphene is another allotrope of carbon that is one atom thick plan sheet of sp and sp2 bonded carbon atoms arranged in crystal lattice. Different from graphene, graphene is semiconductor. Graphene is a semiconductor with direct band gap. The third one is graphitic carbon nitride. Graphitic carbon nitride is a two-dimensional crystal with a van der Waals layered structure van der Waals layer structure and is considered to be the most stable allotrope of the various carbon nitride material. The crystal structure of GC3N4 can be described as a hexagonal carbon framework with N substituted carbon through the sp2 hybridized carbon. Due to its band gap that is 2.7 electron volt, the semiconducting properties of GC3N4 makes it very suitable for photocatalytic process. The nitrogen-rich carbon framework of GC3N4 is another important feature for electrocatalysis. The fourth one is hexagonal boron nitride, which called white graphene. The H hexagonal boron nitride is an insulator which is a with a thickness dependent band gap. The electronic and optical devices HBN nanosheets have been used as dielectric substrates for graphene and MS2 based heterostructures. For the electrocatalysis, HBN need to be activated. The fifth one is black phosphorus. It is a layered semiconductor with an orthorhombic crystal structure. One phosphorus atom is covalently bonded with another three atoms to form puckered honeycomb structures in a single layer. The three bonds take up all the valence electrons of phosphorus, resulting in a band gap of 2 electron volt, which can be tuned by controlling its thickness. Compared to its bulk form, two-dimensional BP nanosheets synthesized by liquid exfoliation techniques possess increased exposed active sites and surface area. Therefore, the intrinsic benefits of these ultra-thin laminar structures can promote the development of BP for efficient electrocatalysis. This is metal organic framework. It is a porous crystalline compounds consisting of metal ions or clusters coordinated to organic ligands forming bulk structures. MOF is important in electrolysis because of its tolerable structures, high porosity, and large surface area. The crystal structures of MOFs can be varied from 3D structures to 2D layered structures. Compared to their bulk form, 2D MOFs have highly accessible active sites for electrocatalysis. 2D MOFs have been applied in many electrocatalytic processes including the HER and OER. Another important application of MOFs is to use the synthesis of metal single atom catalysis. Metal single atom catalysis demonstrate unique properties in a wide variety of heterogeneous catalysts and electrocatalytic process. And the last one is transition metal oxides. Two-dimensional transition metal oxides present great, great, great potential in electrocatalysis due to their low cost, high stability, and tunable activity. The two-dimensional transition metal oxides are active for various electrocatalytic reaction in the water and carbon cycles. Most of the two-dimensional transition metal oxides can be used as electrocatalysis directly without further modification. Thank you.
Hello everyone, my name is Agus Baharudin, and today I will introduce my topic entitled Nanotechnology Application in Energy. Before starting, I would like to outline my presentation first. In the first, we will talk about what is nanotechnology, and then nanotechnology in solar energy harvesting, nanotechnology in wind energy, and then conclusion. Nanotechnology is an enabling technology that offers a wide range of tools to solve energy-related problems. Since the developing parts and appliances are smaller than 100 nanometers, they offer new ways to catch, store, and exchange energy. As you can see in the slide, this is the length scale of different objects from 0.1 nanometers to 10 millimeters. Recently, many researchers have developed and advanced this kind of technology due to the enormous of advantage. For instance, physical, chemical, and biological properties at the nanoscale differ fundamentally and significantly from those of individual atoms and molecules or bulk matter. Then, in fact, that the particle size plays a very prominent role due to the fact that characteristics of the materials are inevitably affected at the nanometer scale, which means that by using the nanotechnology, we can increase the material properties of an object to have better material properties such as better lighter material, stronger material, and even more. But when we talk about the energy, the human reliance on the on the fossil fuel energy have increased over the past years, which makes the new renewable energy will play a crucial role in our future energy. One of the source for the new renewable energy is come from the solar energy. Solar energy is the radiant light and heat from the sun that is captured by a variety of technologies such as solar power to generate electricity, solar thermal energy including solar water heating, and solar architecture. As you can see in the slide, this is one of the technology to capture to convert the solar energy into the electricity, or we will call it solar panel. One of the most common solar panel is photovoltaic solar cell. Solar cell is the photovoltaic device that convert the light energy from the sun into electrical energy by using the principle of photovoltaic effect. While photovoltaic effect itself is a photogenerations of charged carriers in light-absorbing materials. In simple, this solar cell will convert the light energy become the electrical power so that we can use this electrical power for the different purposes. In the market, solar cell have several types. For instance, the monocrystalline silicon cell, polycrystalline silicon cell, and amorphous silicon cell. However, in its applications, some solar cells still have some limitations. For instance, solar cells are quite expensive, and then the electricity productions having by the solar cell will be affected by the air pollutions and weather. And need large place to produce more efficient power supply, less efficient and costly equipments, and as well as, and then need energy storage to store electricity. To overcome these problems, the nanotechnology can play a role to solve this problem. As you can see in the slide, this is the new generations on the solar cell, or we will call a thin film solar cell. A thin film solar cell itself is a second generation solar cell created by depositing one or more thin layers of photovoltaic material onto a substrate. And then film thickness range from a few nanometers to tens of micrometers, which is significantly thinner than the thin competitor films technology to the conventional one. These thin film solar cells have some advantages. For instance, solar cells coated with silicon thin film of 1 nanometer are most efficient and offers more absorption of photons from the light. And then thin films improve performance by 60%. And to lower the cost productions, this thin film solar cell will use roll-to-roll fabrication method. And then increasing nanotechnology can be used to increase solar panel efficiency by using nanostructure anti-reflections coating on solar panel. As you can see in the slide, in its applications, not all of the sun comes through the solar panel will be absorbed and converted into the electricity by the solar panel, and this phenomenon will decrease the power capacity having by the solar panel. And to solve these problems, to solve these problems, we can use the anti-reflective coating. Anti-reflective coating or anti-reflections coating is a type of optical coating applied to the surface of lens and other materials devices to reduce the reflections. This improves the efficiency of the system since less light is lost. Some material that can be used as the air coating is aluminum oxide, silica, titanium dioxide, and zinc oxide. Further, to improve the solar panel efficiency by using the self-cleaning solar panels. As previously mentioned before, one of the problems having by the solar panel is the electricity productions will be affected by the air pollutions and weather conditions, which means that if the solar panel is if the solar panel located in the outside conditions, it will make the solar panel have chance to get dirty on or dusty, and then these conditions will prevent the solar panel to absorb more sunlight, which make the conventional solar panel require more cost to do the cleaning and maintenance. And then this dirty solar panel can reduce power generations. However, this problem can be solved by using the self-cleaning solar panels, or we will call the super hydrophobic surfaces, to improve the performance of solar panel. So by using this method, the solar panel, the dust material will not be able to stick in the solar panel surfaces, and then prevent the solar panel, and then it will increase the power generations having by the solar panel itself. The next is nanotechnology in wind energy harvesting. Wind power or wind energy refers to the process of generating mechanical power or electricity using the wind. And then this wind turbine converts the wind's kinetic energy into mechanical energy, and this mechanical energy can be utilized for the specific purpose, or it can be converted into the electricity by a generator. As you can see in the slide, this is the constructions of the wind power turbine or wind power generator, including the blades and then the generator itself. And then, as you can see in the slide, this is the power productions flow chart having by the wind turbines generator. But how can nanotechnology can be applied for the wind turbines? As you can see in the slide, this is some of the application of nanotechnology in the wind turbine. In terms of weight, using nanocomposite materials with excellent strength to weight and stiffness to weight ratio can make constructions of wind turbine more robust, especially for blades. And then in terms of energy losses, using low friction coatings and nanolubricants provide means to reduce energy losses in the gearbox, and thus increasing energy capturing efficiency having by the wind turbine. And then in terms of blades, carbon nanotubes developed to make blades stronger and lighter for improving energy efficiency. And in terms of lifetime, using nanopaints can increase the wind turbine lifetime. Conclusions. First, nanotechnology plays a crucial role in advancing current energy harvesting technology to its full potential. And second, the use of nanostructured materials in solar panel can increase power capacity, resulting in increased efficiency and decreased production cost. And in wind energy, nanotechnology can be used to reduce the overall weight of wind turbines by employing nanostructured materials and to reduce frictions by employing nano coatings and nano lubricants, thereby increasing the wind turbine's power output and reducing production cost. Thank you.